Modern physics tells us that there are four primary forces or interactions in the universe. There's the gravity interaction, the electromagnetic interaction, the weak nuclear interaction, and the strong nuclear interaction. We've seen the gravity force and the electromagnetic force. And when we talk about protons and neutrons binding together in the nucleus, that's the work of the strong nuclear force, which we've so far called the nuclear force. We're going to learn how these operate between even smaller subatomic particles, quarks and leptons. So let's say you had an up quark and it was traveling along a straight path like this. What might cause this thing to deviate from its path? Well, if you put an up near a down, even if this is going like this and the down is moving like so, they are attracted to each other, so they curve toward each other, and they travel along that path. We can explain this curving and this attraction using the strong nuclear force. It acts between quarks. Now, one of the ways to represent that force is using a vector. And as they pass, they are attracted, and the vector arrow shows the attraction from this force. But there's another way to mathematically represent this force. Instead of using vector arrows, we can talk about the two exchanging a particle as they go. Exchanging that particle is the mechanism by which they interact at all and pull on each other. So we're describing this force via an exchange particle, which is called a gluon. There are other exchange particles besides the gluon. This is the exchange particle for the strong force. So let's look at a different force. If you take two electrons, they're negatively charged and they repel. So they bend away from each other as they pass by. We can explain this again using the mathematical concept of a vector. So we're representing the force with vectors now. And the vector shows that they're getting pushed away, and that's why they deviate away from their straight line path. And so these arrows represent the repulsion from the electromagnetic force. But instead of describing this force using vector arrows, we could again use the concept of exchange particles. The way these two interact as they pass and as they push on each other, the way that they interact and exert that push is via exchange particles. Again, why are we talking about exchange particles instead of force vectors? Well, exchange particles are an incredibly mathematically robust concept in particle physics. So we are describing the interaction not with vectors, but we are using an exchange particle, which is the photon. This is the exchange particle for the electromagnetic force. So each force has its own exchange particle that we use in particle physics to describe the interaction. The strong nuclear force has gluons, which we represent sometimes with a G. We can actually assign different drawings for the different exchange particles. Gluons are often shown like this. They look kind of like a spring. The weak nuclear force, its exchange particles are the W+, W-, and Z bosons. The bosons we represent with a different line, like this. So this is kind of odd. The weak nuclear force has three different exchange particles, W+ bosons, W- bosons, and Z bosons. So what's the difference? This here represents the charge. The W+ boson, the exchange particle, actually carries some charge, whereas this one is neutral. Okay, how about the electromagnetic force? Its exchange particle isn't a gluon, not a boson like this, but simply a photon, which we represent with the gamma symbol. Photons we can draw using this kind of a squiggly line in our pictures. We're not going to talk about the gravitational force because no one knows what those exchange particles are. In fact, we don't even know if gravity fits in this type of picture. It is very much still an open question. Now, let's connect these forces to the different types of particles like quarks and leptons. We'll start with quarks. That includes up, down, top, bottom, charm, and strange. Quarks are the most versatile. They can interact via the strong force, This must be a gluon because the gluon mediates the strong force. But they can also interact via the weak force. So this would have to be a W boson or a Z boson. And finally, they can interact via the electromagnetic force. So this would have to be a photon. These are the ways quarks interact. So how about leptons? Well, there's kind of two categories. There are leptons that have charge and leptons that don't have any charge. The ones with charge are the electron, tau, and muon. The ones that don't have charge, the three neutrinos. So what are the interactions that leptons engage in when they have charge? There's two. Charged leptons can interact with the weak nuclear force, so this would have to be a W or Z boson. They can interact via the electromagnetic force, so this would have to be a photon. Uncharged leptons are the exact same, except because they have no charge, they cannot participate in the electromagnetic force. So all they can do is interact with W and Z bosons via the weak nuclear force. Now, this picture shows a very, very limited view. You actually can have interaction between charged leptons and uncharged leptons, but they would only be able to interact using the weak nuclear force because they both participate in the weak nuclear force. These interactions, by the way, that we're referring to, they're more than just repulsion and attraction. The other type of interaction would be decay. And through decay, particles can change from one type to another.